Welcome back to Differential Equations. In this video, I want to introduce you to Fourier Series. Before we get into it, let's take a look here. Remember, a series is a summation, specifically a sum that has infinitely many terms. And a Fourier series specifically is a sum that involves sine of n pi x over L and cosine of n pi x over L. We've seen previously, talking about boundary value problems, that sine of n pi x over L and cosine of n pi x over L are useful things to have. And so a Fourier series is going to be a way of combining these things together and getting some more information and being able to expand what we can do with our solutions to boundary value problems. Before we can get there, though, this idea does rely on an awful lot of theory. If you have previously taken a course in linear algebra, most of these ideas should be very familiar to you. If you've not taken a course in linear algebra, I'm very well aware that I'm going through all of this quickly. Honestly, most of the stuff that I am flying through doesn't matter all that much. But understanding how and why we can do some of these things is going to be important. So, we're going to start off with a couple of piecewise continuous functions. Remember that a function that is piecewise continuous means that it has regions where it is continuous, and then possibly jumps where it goes from one point to another and then becomes continuous again. But there are only finitely many of these jumps, and except at those points the function is continuous. We want that condition here because that forces the integral negative a to a of f of x dx, g of x, and f times g to all be defined. It's sufficient but not necessary that this is true in order for the integral to be defined. We could have had more general conclusions, but this is going to be a very powerful one for us. And our goal here is to define what it means for functions to be orthogonal on the closed symmetric interval negative a to a. In order to do that, we're going to define a calculation called the inner product. And in this space, the inner product is just going to be the integral from negative a to a of the product of the two functions. Whenever this integral is equal to 0, we say that the functions are orthogonal. And if you are taking, have taken, or even will take a course in linear algebra in the future, this idea of orthogonal really does come down to the same definition of orthogonal you think of in geometry. They are somehow perpendicular to each other. There's a lot of value that you can get out of linear algebra for knowing that functions are orthogonal. Again, I'm just going to take this all as assumption and build up the tools that we need. But I want to give you enough background information on how and why we're doing this so that if you have taken a course in linear algebra, or if you do take a course in linear algebra in the future, these connections should make sense to you. All right. So our goal is to look for functions that are orthogonal. We're going to do that by integrating their products. Okay. Our first theorem, I claim that for integers m and n that are not equal, and for real constant L, the sign of m pi x over L and the sign of n pi x over L are orthogonal to each other. In order to prove this theorem, I guess the best way to approach it is to just directly start integrating. So we're looking at the integral from negative L to L of sine of m pi x over L times sine of n pi x over L dx. In order to evaluate this integral, we're going to use a product to sum formula. So something that you probably saw when you took a course in trigonometry and probably haven't thought of in over a year. Oops. If you have 2 times the sine of u times the sine of v, that's the same thing as the cosine of u minus v minus the cosine of u plus v. Right, so if you have the product of sines, you can turn it into the difference of cosines. And with that, we can rewrite our integral from negative L to L. It's now going to be the cosine of m pi x over L minus n pi x over L minus the cosine of m pi x over L plus n pi x over L. And then there was this 2 over here that we didn't have before, so we'll just divide that into the other side, and it'll turn into a 1/2 in front. Great. Now inside these arguments, we've got pi x over L's that keep repeating. So we can clean this up a little bit. 1/2 integral from negative L to L of cosine of m minus n pi x over L minus cosine m plus n pi x over L. The next step is a little bit tricky. For my next step, I'm going to remind you that for an even function, the integral from negative a to a of f of x dx is the same thing as twice the integral from 0 to a of f of x dx. Right? Remember, an even function is one that is mirrored on the positive and negative values of x. So going from negative a to 0 and going from 0 to a is exactly the same thing. So we just do that twice. And cosine is an even function. So I can do exactly that here. We have that 1/2. We'll now multiply it by 2. That's going to make life really nice. And at this point, I'm also going to start getting lazy and not put all of my parentheses in. This kind of construction happens so often that it's well understood amongst mathematicians that cosine of some fraction, that fraction is the thing that's supposed to be the argument of the cosine. You don't need to surround it in parentheses. Now, actually performing this integration is a lot easier than it looks at first glance. Because m minus n times pi over L and m plus n times pi over L are just constants. So we have integral cosine a times x. And the integral of cosine a times x is 1 over a times the sine of a times x plus a constant of integration, but we're dealing with definite integrals here, so we don't need to worry about that. All right, so my 1/2 multiplied by 2 are going to cancel each other out. I'm going to have L over m minus n times pi times the sine of m minus n pi x over L minus L over m plus n times pi times the sine of m plus n times pi times x over L. Evaluate that at my limits of integration. Now watch what happens when we plug in the limits of integration. If I plug in x equals L, then I'm going to have an L over L that's going to cancel each other out. And when I plug in the limit of integration x equals 0, then the whole thing is just going to become 0. So we have L over m minus n times pi times sine of m minus n pi minus L over m plus n times pi times sine of m plus n times pi. There's my upper limit of integration. Subtract from that my lower limit of integration. Sine of 0 is 0. So those go away. And then up on the earlier line, sine of any integer multiple of pi is also 0. We took great advantage of that in a couple of videos earlier. Sine of any integer multiple of pi is 0. Sine of 0 is 0. So we get 0. And the definition of orthogonal functions is that this integral comes out to 0. We did the integral, we got 0. We must have orthogonal functions. I don't know about you, but certainly the first time I saw this, my immediate follow-up question, looking at the statement of that theorem, was, well, what happens if m equals n? Right, if I jump back, remember that the statement of the theorem was if we have integers m not equal to n and a real constant L, then these two functions are orthogonal. But we saw that that is true. And so the next question is, what happens if we tweak that a little bit? What if we didn't have m not equal to n? What if they were, in fact, the same value? Well, in that case, we are looking at the integral from negative L to L of sine n pi x over L times sine n pi x over L and we'll start off the same way we did before. We're going to rewrite this using that product to sum formula. We'll have a 1/2 in front, and we will have cosine of n minus n times pi x over L, and we'll have cosine of n plus n pi x over L. N minus n is 0, so this first term is actually just cosine of 0. And then n plus n we can just write as 2n. And then from there, cosine of 0 is the same thing as 1. And 1 is in fact an even function. So we can use the same trick that we used previously here as well. We can double it, changing the lower limit of integration from minus L to 0. 2 times 1/2 just cancel each other out yet again. And so, integral of 1 is x. Integral of this cosine is going to be L over 2n pi times sine of 2n pi x over L. Our limits of integration are 0 and L. So we have L minus L over 2n pi sine of 2n pi as our upper limit of integration, and then 0 minus L over 2n pi sine 0 as our lower limit of integration. That's still 0. Any integer multiple of pi, sine of that angle is 0. Sine of 0 is also still 0, so we've got 0, 0, 0, but this is not. So we end up with L. All right. So when you have the same function, it's not orthogonal to itself. I guess thinking about that geometrically, right? If you have a line, the line is not perpendicular to the line that you started with, but it's good to know. All right, I'm not going to go through the calculation again, but we're going to see a very similar result here. If we use cosines instead of sines, we have the same result. Theorem 2 says that for integers m not equal to n and real constant L, cosine of m pi x over L and cosine of n pi x over L are orthogonal. And then theorem 3 notice in this case, we don't need that m not equal to n. For any integers m and n, and real constant L, then this time we're going to mix our functions. Sine of m pi x over L and cosine of n pi x over L are also orthogonal. I don't really think that you're going to gain that much by going through these proofs as well. Right? They follow the same pattern as the first one that we've already done. And that's an awful lot of setup. We know that these kinds of functions, cosines and sines of some integer times pi times x divided by some constant, show up when we're solving boundary value problems. But the fact that these functions are orthogonal to each other gives us a very powerful tool. In linear algebra, we call this a basis set, and we can describe any function in the span of the basis as a sum of the basis functions. If that doesn't make any sense to you, again, that's okay. You're not expected to have seen linear algebra in the past, but if you are taking linear algebra, there's a nice callback to something that is very important in that class that keeps coming up all over the place in mathematics. For our purposes here, though, we have Fourier's theorem, which tells us that for any function f that is piecewise continuous on the interval from negative L to L, Fourier's theorem tells us that for any piecewise continuous function f on the interval from negative L to L, there is a sequence of constants a(n) and b(n) such that f of x is equal to a0 over 2 plus the sum, n goes from 1 to infinity, of a(n) times the cosine of n pi x over L plus bn times the sine of n pi x over L. So the value of a Fourier series is that if you have any piecewise continuous function, you can in fact represent it as a Fourier series in some way, shape, and form. And actually, we can go one step further. It must be the case that for each n, a(n) is equal to 1 over L times the integral from minus L to L of f of x times cosine of n pi x over L. And every bn, for every n, has to be equal to 1 over L times the integral from negative L to L. Come on, roll up, there we go. F of x times sine n pi x over L. So we know that this series must exist, and in fact we even have forms for figuring out how to figure out the constants. This video is running on long enough, so I'm not going to try to show you how to use these just yet. But in a future video, we're going to look at how we can take arbitrary functions, plug them in here, find a Fourier series to represent that function, and use that Fourier series to make some interesting insights into how the function might work. For right now, though, what I want you to do is I want you to take this function for f of x equals a0 over 2 plus the sum, n goes from 1 to infinity, a(n) times the cosine of n pi x over L plus bn times the sine of n pi x over L. And I want you to evaluate the integral from negative L to L of f of x times the sine of 3 pi x over L. We know from what it says right up here, this should be, if I put a 1 over L in front of it, it should give me bn, where n is equal to 3. But I want you to see that that's what's going to happen by plugging this into that original, or plugging that generic form into this. When you do that, you're going to get a bunch of integrals that are going to expand out, right? So split up the integrals over the addition, and then use all of the results about orthogonality that we talked about in this video, and most of those integrals are going to go away, and life is going to be good. All right, take a couple of minutes to play around with that, and I'll see you in the next video.